4.5 billion years ago, Earth literally had the worst day imaginable. A planet the exact size of Mars slammed right into the proto-Earth at thousands of kilometers per hour. Earth survived. The other planet? Yeah, it absolutely did not. Their shattered, combined debris coalesced in orbit and became our moon. But this wasn't just a cosmic fender bender. This single catastrophic collision may have actually given us our magnetic field, our axial tilt, our oceans, and maybe even the very conditions for life itself.
Welcome back to the GeoVault 77 Deep Time Earth Science series. I am so thrilled you're joining us today. In this explainer, we are diving into the absolute ultimate origin story for our world, the birth of the moon. Pretty much every geological event we've discussed or ever will discuss owes its stage to this one unimaginably violent moment.
So here is our roadmap for this explainer. We'll start with a problem with the moon, then the giant impact hypothesis itself, the hard evidence, what the impact actually gave us, and finally, how this acts as the prequel to Deep Time. Let's get right into it.
Chapter 1. The Problem with the Moon and Centuries of Failed Theories.
You know, for almost all of human history, the moon's origin totally defied the laws of physics. Before the mid-20th century, we basically had three theories, and spoiler alert, they all completely failed. First up was the capture theory, the idea that Earth just grabbed a passing moon. But the orbital dynamics for catching a body that massive? Basically impossible. Then George Darwin, yes, Charles Darwin's son, proposed the fission theory in 1898. He thought a fast-spinning, molten Earth just flung off a giant chunk. But the physics didn't work at all. Newtonian mechanics couldn't trace the moon back to Earth's surface. And lastly, the cove formation theory argued they both formed together from the exact same dust cloud. But if that were true, they'd have the exact same composition. And they definitely don't. The moon has this tiny little iron core compared to Earth's massive one. So scientists were totally stuck.
Well, that all changed with a very specific number, 382. That is the exact number of kilograms of lunar rock brought back by the historic Apollo missions. These rocks finally offered a way to solve the old mystery. But you know what? They ended up creating a completely new, massive paradox instead.
When scientists actually analyzed those Apollo samples, they found something completely baffling. The moon's rocks have nearly identical oxygen isotope ratios to Earth's rocks. I mean, they are isotopic twins. But, and here's the massive catch, the moon's overall composition is totally different. It's almost entirely missing the iron that makes up so much of Earth's bulk. So, how on earth can it be made of Earth material but completely lack its iron?
That brings us to Chapter 2, the Giant Impact Hypothesis, a 1975 audacious idea.
To solve this ironclad paradox, scientists had to think way outside the box. In 1975, two researchers, Hartman and Davis, proposed a radical new model. They hypothesized a Mars-sized impactor that hit proto-Earth roughly 4.5 billion years ago. They later named it Theia. And honestly, it's a perfect name. In Greek mythology, the Titan Theia is literally the mother of the moon goddess Selene. They figured Theia drifted into a chaotic orbit and just crashed right into us.
But to really grasp what happened next, we have to talk about the Roche limit. This is the orbital distance inside which a celestial body would just be totally torn apart by the tidal forces of the planet it orbits. When Theia hit, it wasn't a dead-center head-on collision. It was a glancing blow at a roughly 45-degree angle.
And that glancing blow? That is exactly the key that solves our iron paradox. Because Theia was utterly destroyed on impact. Its super-dense, metallic iron core just sank straight into the young Earth's core. Meanwhile, all the lighter, shattered iron-poor mantle material from both Theia and the outer layers of Earth got blasted outward. It formed a massive debris disk, a giant ring of molten rock, just safely beyond the Roche limit, where it could survive and start clumping together.
Which leads us to Chapter 3, the evidence, where data finally meets supercomputing.
A wild hypothesis is great, but how do we know this actually happened? Well, when modern astronomers run computer simulations of the Theia impact today, the data perfectly reproduces the Earth-Moon system we actually observe. Just look at the density and iron core fraction. Earth's core is 32% iron, but the Moon's is less than 2%. The impact perfectly explains why Earth swallowed all the heavy iron and the Moon formed from the much lighter silicates. Plus, the Moon's volatile content is incredibly low compared to Earth.
And that missing volatile content perfectly matches up with something called isotopic similarity. Specifically, when we look at elements like zinc, which separates out when it evaporates,
Lunar rocks are depleted of overall zinc, but they have heavier isotopes than Earth rocks. This is a massive smoking gun. It proves the material that formed the moon was subjected to absolute extreme heat. We're talking about a scenario where, in the first few hours after the impact, the debris disk was literally a planet-sized fog of rock vapor boiling at 8,000 degrees Celsius. The lighter volatiles simply boiled right away into deep space.
Okay, so exactly when did this cosmic demolition derby take place? Well, the timing was heavily debated for a very long time. But recent analysis of lunar pharonoid anorthosites, which are basically the rocks that form the moon's original crust, using rubidium-strontium isotope dating, has pinpointed a very specific number, 4.502 billion years ago. That places the catastrophic Theia impact at about 65 million years after the birth of the solar system itself.
And the pacing of the aftermath is honestly breathtaking. So 4.502 billion years ago, the impact happens. Then, incredibly, simulations show the entire debris disk coalesced into the moon in just 100 years, not millions of years, just one single century. By 70 million years post-impact, the lunar magma ocean had solidified. And we even have evidence of another global remelting event around 150 million years later.
Now for Chapter 4, what the impact gave us, and its consequences echoing through history.
Why does all of this matter to us today? Because the consequences of the Theia impact absolutely did not end 4.5 billion years ago. When Theia hit, it knocked Earth right off its axis, giving us the 23.5-degree tilt that provides our stable seasons. Right after the impact, Earth was spinning so incredibly fast that a single day lasted only 5 or 6 hours. Imagine trying to get anything done. But the tidal interaction with the moon's gravity has been acting as a brake ever since, slowing us down to our comfortable 24-hour day. Theia also gave its iron core to ours, which enlarged it and gave us a strong magnetic field. Add to that our ocean tides and the moon's role as the cultural, religious, and navigational bedrock of human history, and it's clear just how much we owe to this one event.
Finally, Chapter 5, Prequel to Deep Time, the Geological Big Bang. In the context of our Deep Time series, this impact is the absolute prequel to everything. Notice how flawlessly this sequence sets up the rest of Earth's history. Step 1. Theia stabilizes our axial tilt and creates tides. Without those tides, Step 2. Earth's first life, utilizing nutrient-rich tidal pools 3.5 billion years ago, just doesn't happen. Step 3. The Great Oxidation Event thrives because of the stable climate provided by our new axial tilt. And Step 4. Even the massive asteroid impacts of the late heavy bombardment were hitting a crust that had already been completely primed and remade by Theia.
Which brings us to a final, profound thought. Every tide, every full moon, every stable season, every single chapter of our deep time history traces back to that one solitary, magnificent collision. So the next time you look up at the night sky, ask yourself, if Theia had missed us by just a fraction of a degree, would anyone even be here to look up at all? Thanks for joining me for this explainer. Keep looking up and stay curious.